Hi guys, in this video we'll continue our look at elimination reactions. And we'll pick up here with section E where we left off at. We briefly introduced this in the last video. But the question here is, when there are multiple beta elimination products possible, which one will be formed? In the top reaction, there's only one beta elimination product possible because there's only one beta carbon. And thus there's only H's on that one beta carbon. Both of them are identical. We can only put the double bond in between the carbon with the leaving group and this beta carbon, so it must go there. Okay? Particularly if we're doing an E2. We'll talk about rearrangements. Of course, if we're doing a carbocation chemistry, we could have a rearrangement and the double bond can end up in other positions. Now, if the double bond is put between these two carbons, it's there, and there's no stereochemistry. That alkene is not stereogenic. So that's the only theoretically possible product here. But in this reaction, there's actually three, because we could put the double bond in on this side, because that's a beta carbon compared to that alpha carbon. And here it is, the double bond on that side. But this product, this alkene is stereogenic. It could be E or Z. But we could also put the double bond in between the alpha carbon and the beta carbon on this side. That would be the same as above. This product is not stereogenic. So which alkene will be formed in this second reaction? Okay, a couple of things to look at. Number one, the most substituted alkene is the thermodynamic product in these reactions. And the thermodynamic product is called the Zaitsev product when you're doing an elimination reaction. Now, it's always the major product when you're doing an E1 elimination. Always. But not necessarily the case when you're doing an E2 elimination. Sometimes when you're doing an E2 elimination, you can get the less substituted alkene. And the less substituted alkene is called the Hofmann product when you're doing eliminations. So let's look at an example. If you take this alkyl halide and water, we're probably going to have to heat this. We can show an elimination product. We can show formation of essentially HBr. We eliminate HBr, but we showed here the water taking the H and the Br minus existing by itself. But the product here, I'm showing the more substituted alkene. That is, I'm putting the double bond in between this carbon, this beta carbon, and the alpha carbon. And we're not putting the double bond in between this carbon and this carbon. We're not making that product. This would be a monosubstituted alkene, the less substituted product. This is your most substituted product. And remember, it's always the major product in an E1 elimination. Now, there's an error here. I say E isomer, not Z. Let's add this. When possible. Because this alkene is not stereogenic. You may have already noticed that. And so we can't label it as the E isomer. But if it was, we would argue that the E isomer should be favored because the E is typically going to be more stable than the Z. Up here, E and Z. Why? Well, with Z, typically we see that the bigger alkyl groups are on the same side, and when these alkyl groups are cis to each other, there's more steric interaction. This is like syn versus anti. The groups being opposite to each other is going to be a more stable arrangement, and so typically E is your favored product between the two stereoisomers. Okay, this would be an E1, right? Why is this E1? Well, there's no strong base. Mechanism, if you want to remember your E1, what's the first step of your E1? All right, you can look back, you can pause, you can look back. But the first step is leaving group just leaving. Ionization. To give carbocation. Then we remove the H from the beta carbon, but which one? That one or this one? Two different beta carbons. Going to remove it here. Okay, we got Br minus. We could use Br minus to take the H. We would make the alkene plus HBr. But how does HBr exist in water? It's going to be ionized like this. So we could also just simply show water taking the H, electrons moving in. That would give the alkene product, H3O plus, and the Br minus would just sit there. Summary, E1 always gives the most stable alkene as the major product. What about E2? Well, with E2 it varies depending on the base used and orientation of the groups in the starting material. Let's first look at different bases used. Same substrate, but here we're going to use a strong base because E2 requires a strong base. Here we use hydroxide. If you use hydroxide, which is a non-sterically hindered base, it's very small. It's not sterically hindered. It will take the H from the beta carbon over here. Concerted mechanism. Base takes the H, electrons move in, leaving group off, and you will get the most stable product. The more substituted alkene, just as above. In this case, we form water here and the leaving group left. The thermodynamic product is easily formed here with an unhindered or non-sterically hindered strong base, which has no problem abstracting the more hindered beta hydrogen. Because actually, the hydrogen that we're removing here to give the more substituted alkene over here is between these two alkyl groups. So it's the more hindered or more crowded beta hydrogen. The other beta carbon, the H that's on the other beta carbon, is less crowded. It's not between two alkyl groups. So, see the difference between your two different beta hydrogens here. A small base has no trouble taking the more crowded H to give the more thermodynamically favorable product, to give the Zaitsev product. But if we use a sterically hindered base, it's another oxygen anion, but here we have tert butyl oxide or tert butoxide, or sometimes just called T-butoxide. These alkyl groups nearby make this sterically hindered. We first introduced that back in the substitution handout when we looked at nucleophiles. And we said that the T-butoxide is often used as a non-nucleophilic base for E2 elimination. But why non-nucleophilic? Because of sterics. Steric crowding is going to make this a poor nucleophile. It also influences the elimination reaction because of sterics. It can't get to the more crowded H, and instead it more readily takes the less hindered H. And so we can explain this as taking this H is faster. It's also easier. I mean, that's why it's faster. Easier / faster. But that doesn't lead to the most stable product. It actually leads to the less stable product. So it's not the thermodynamic product, but instead we say it's formed faster or easier. Faster refers to rate, thus we call this the kinetic product. In the context of elimination reactions, remember we call it the Hoffman product. It's more likely to be formed when using a sterically hindered strong base and so this is a case where we can get the less substituted alkene, but only when we're doing an E2, because remember, E1 always gives the more substituted, always gives the Hoffman. You can only get the, Zaitsev. Always gives the Zaitsev. You can only get the Hoffman as a favored product by doing an E2 and using a sterically hindered base. Okay. The second thing to look at here is the stereochemical requirement for an E2 elimination. This is another reason we may not get the thermodynamic product. All right, important statement here. In an E2 elimination, the leaving group and the beta hydrogen that is being abstracted must be coplanar. With anticoplanar, also known as antiperiplanar, being very much preferred over syn coplanar. Now we'll explain these terms and illustrate them here. But this is a requirement for the E2 elimination. As a result of this requirement, sometimes the less desirable, I don't like that term desirable, the less stable, the less thermodynamically stable Hofmann product is formed in an E2 reaction because the leaving group and beta hydrogen leading to that product could become antiperiplanar, while they could not do so to give the more stable Zaitsev product. We'll show examples. Now this requirement must also be considered to determine if the elimination product, that is the alkene, will be E or Z. Now this requirement only applies to E2. In an E1 mechanism, you do not have this requirement. Of course, in an E1, the leaving group and the beta hydrogen are not removed in the same step anyhow, right? Okay, examples of anticoplanar and syncoplanar. Here's just a 2-carbon molecule, leaving group and beta hydrogen. These are anticoplanar. Okay, about this bond, one is one way and one's the other way. If you remember Newman conformations, okay, the front carbon's here, the back carbon, we can't see it, it's hidden. But on the front carbon, the bromine is straight up. On the back carbon, the H is straight down. And so we said that the H and the bromine are anti here. These are the same view, except here I'm looking toward the side. Here I am looking, well, I'm standing over here, right? Looking through there. This carbon's in front, that one's in the back. Front carbon bromine's going straight up, back carbon H is going straight down. So this is the same molecule, 2 different views. This would be syncoplanar. All right. Anticoplanar, very much preferred. Also called antiperiplanar. Now it's preferred. That doesn't mean syncoplanar cannot work. But it's typically better for the H and the bromine, let's call it leaving group. The H and the leaving group, no matter what the leaving group is, for them to be anticoplanar. See, this is the plane. If you got a piece of paper here, there's the plane. They're both sitting on that plane. Okay? Okay? Like a plane of paper here. All right? My hand. They're both in that plane. Now with rings, here, remember rings, chair conformation? The H and the bromine here are anticoplanar. Because if you just look at them, here, the bromine is straight up, the H is straight down, and that is a plane through there. All right? If you look at a model there. Now, importantly, with 6-membered rings, the leaving group must be axial to be coplanar with a beta hydrogen. And this hydrogen on this beta carbon is the one that is anticoplanar with the bromine. This one is not. if this does a ring flip and the bromine goes equatorial, okay, there is no beta hydrogen anticoplanar to this bromine now. Look next door, okay? And if you had a model, you would see it better. This H is straight up. This bromine would need to be straight down. And the bromine and that H are also not. They're sort of diagonal to each other. But when the leaving group is axial, the axial beta hydrogen is anticoplanar. Okay, let's use this information to predict the product here. First off, what type of reaction are we doing here? We have a tetrahedral carbon with a leaving group. Okay. We can do possibly substitution or elimination reaction. We have hydroxide. Let's get rid of this potassium. It's hydroxide. Isopropanol. Are we even doing an elimination reaction? We have a strong base / nucleophile. Thus, our mechanism equals, well, it's going to be bimolecular, right? Remember, we summed it up with strong nucleophiles or bases, okay? Reaction will always be bimolecular, either SN2 or E2. Because strong nucleophiles or bases, they're like bullies. They stick their nose in. Here I come. They're not going to wait on any ionization of the leaving group. SN2 or E2. Okay? But can you do SN2 on this molecule? The leaving group is on a tertiary carbon. Well, from our substitution handout, we said we never do SN2 with a tertiary halide. Never. This looks like a good old E2 elimination. Okay, why don't we do this? What are the theoretical products here from elimination? I'll do it here. Let's see. How many different beta carbons do we have? Well, that's the alpha carbon. That's the carbon with the leaving group, right? Over here would be beta, and there's an H going back. Let's call that HA. And here's another beta carbon. There's no H here, though. It's 3 methyls. But here's another beta carbon, alpha beta. And there are 3 H's here. I'm just going to draw one in. It's not chiral. Call that HB. Okay. If we abstract HA, the double bond is going to be between that carbon and the carbon with the leaving group. Carbon on the left will have an ethyl and a methyl. Carbon on the right will have a methyl and a T-butyl. That's if we do an E2 elimination and abstract HA, electrons in, kick off leaving group, double bond here. But this alkene is stereogenic. I just randomly put the ethyl and the methyl cis to each other. I could also have the two methyl cis, put the ethyl here, tert-butyl here. And this would be Z, and this would be E. Now, if HB was removed or eliminated, we would have double bond between that carbon and that carbon. All right, those are the two carbons. The one with HB, and there's one with the leaving group. The one with the leaving group has, well, we're going to put double bond there. The one over here has a tert-butyl and a carbon like this, and then a chiral here, ethyl. Because if the chemistry takes place between the alpha carbon with the bromine and this beta carbon, no chemistry changes here. That's still a tetrahedral chiral carbon. Over here, the tetrahedral chiral carbon became double bonded, and so it's now planar, and there's no chirality any longer. These two would be considered Zaitsev products, tetrasubstituted, more substituted. This would be our Hoffman product. It's less substituted, it's disubstituted. Okay. Now we're doing E2. What if we were doing E1 here? What if we had different reagents and this molecule underwent an E1? What would be the product? Well, E1 always gives the most stable product, the thermodynamic product. The most stable would be a Zaitsev, and it would be E with the ethyl and T-butyl trans to each other. That's the E1 product. We don't have to think hardly any more about that. But which of these three, is there only three possible? Theoretically? Which of these three, yes, is the E2 product? Okay. Well, we can do our mechanism, but what's the requirement? The HA and the leaving group prefer to be anticoplanar. All right. To see that, I recommend a Newman projection. We learned how to draw Newmans during test 1. Let's stand over here, look through here, and what do I see? I see a methyl coming straight down. Okay, I can clarify that as methyl. I see an ethyl to my right, And I see a beta hydrogen HA to my left. Let's look to the back carbon. I see a T-butyl straight down. It's actually eclipsed. That methyl is right in front of that T-butyl. I see a bromine to my left. It's actually eclipsed right behind that HA. And I see a methyl group coming this way. And it's right behind that ethyl. This molecule, as drawn, is in an eclipsed conformation. Right now, the H and the bromine, they are planar, but they're syn coplanar. I want to rotate this molecule. I'm going to rotate the back. I want to rotate it. I want to put the bromine anti-coplanar. Okay, the front I'm leaving the same. Ethyl, HA. Note that HB is on the methyl. I didn't draw it in. It's on that methyl. I was wondering about it. Okay. In the front, methyl. I'm rotating the back. We'll put the bromine here. That's going to move the methyl on the back here. And the T-butyl on the back it's going to be here. And now HA and the bromine are anti-coplanar. There's the plane, okay? This circle plane coming through there, my hand. They're both lying on that plane, okay? If I want to draw the plane here, consider that a big wall there. They're both in the plane of that wall. All right, but they're anti. All right. And that's how the mechanism takes place. What's the mechanism? The hydroxide takes the H. The electrons in the bond move. You can't see between the two carbons, but they move. Okay, I messed this up because now I can't tell what's on the back when I drew my line there. HA's in the front. The electrons move in here between the two carbons and kick off the bromine, which is supposed to be on the back. Okay, again, I messed up by drawing that line. Kick that bromine off. But the important thing is, look what's on the same side. The methyl groups are on the same side when this takes place. And the T-butyl and the ethyl are on the other side. And bam, concerted all together. Bam, double bond is put in. Once the double bond is put in, the groups are fixed. Methyl's on the same side. Which product is formed? Well, it's going to be that one. The methyls are on the same side. The tert-butyl and the ethyl are on the other side. Once the double bond is put in, again, they're fixed. They can no longer rotate. That's the E2 product. Now we got to be careful here. And I could ask this question. When would that product ever be favored? When would the Hoffman product ever be favored? Well, remember what we say just over here. The Hoffman product, which is the kinetic product, is more likely when using a sterically hindered strong base. Is hydroxide a sterically hindered strong base? No. How to get this product? We would use something like potassium tert-butoxide. And that's often abbreviated, instead of drawing out the T-butyl group, T-butoxide. And potassium tends to be more common with the tert-butoxide anion, much more common than sodium tert-butoxide. Okay. Try these on your own. TEA is triethylamine. Okay. 3 ethyls, triethylamine. If you remember it, we showed in the substitution handout, triethylamine is often used as a non-nucleophilic base, such as for E2 elimination reactions. It's not as strong as a hydroxide or alkoxide, but it is strong enough to do an E2. For this one, I'm going to say show both the Zaitsev and Hoffman products. Okay. Up here, this is the Zaitsev product, not that one. Okay. For this reaction, this was the Zaitsev product. Now we can also consider what the Hoffman product would look like. I did that here. Up here, if you're doing this here, if you're doing E2, you're either going to get one of these. You're not going to get that product from an E2. But you would get that product from an E1. Alright, so for this one, alright, keep in mind, just like here, we have a stereochemical requirement. Also, think about the stereochemical requirement down here. These are rings. Again, remember the leaving group, how it needs to be oriented. So some to work on there. Okay. I'll end this video here. That's a nice little concise topic there of when regioisomers are possible from beta elimination reactions. Which one will we get? That's what we're working on. All right. Give these a try, guys.